all those people who are trying to participate remotely. And some of these people have used up all their allowances already. It's starting to eat into absences.
Hey, everyone. You're going fantastic, I'd say. Ready to get some more math in the brain. Be a little bit more, be marginally more educated, hopefully, by the time I leave this room. So, you will be.
That is assuming that you are leaving this room.
Suppose that ain't a probability. It's a low but non-zero chance.
In the analysis of algorithms, this is called the issue of termination. Does the algorithm actually terminate? Which is a fascinating, idea. When you move on to the theory of computation, or usually there's a class like that as an upper division undergraduate class, and you will start to go into like, that's a good question. Is the program going to terminate? Because if the program doesn't terminate, then you cannot even talk about the correctness of the program. So, all right. So I think we got most people in, and I didn't get any new requests. All right. So I do want to mention that remote participation has an allowance of 3 times, and on top of that, there's also an allowance of 3 absences. So once people use up 3 remote participation allowances, then additional absences would eat into the absences. Is that okay? Does everybody understand what I'm trying to say? Okay, so that means there's a total of 6 possible absences / remote participation. And I think that should cover most situations. Because any more than that, we have a more serious issue, because it's not about whether the absences are actually for good reasons or not. It's just that once people miss enough classes, or once they cannot participate enough times in the class, it becomes really difficult to catch up, especially in a class like this where everything's kind of stacks up. All right. So I'm going to get started. There are 2 things that I want to talk about today. The first one is your next homework assignment, and I will also do the program assignment. I'll give you the solution of that one, and then we'll start with the new one, which is starting with a non-negative or positive exponent of 10. I'll give you the math that you need to solve that problem. And then we'll talk about, we'll move on to talk about the 2 NAND gate, known as the SR Latch. So we'll talk about the SR Latch today, and also how do we analyze a circuit that is kind of tricky, where you have some feedback mechanism, so that how do we keep track of the state of the NAND gates when you have like the output of this thing goes to the input of that thing, but the output of that thing also goes back to the input of this thing. So it seems like it is difficult to analyze, but it really is not that difficult. So we'll talk about that today as well. All right, so I'm going to get started with the class because I think it is start time. Yep, here. 2 minutes, almost close to 3 minutes past the start time. So I don't need this clock anymore. I think Zoom has a little recording that has a little time clock all the way down there. So this maybe just be duplicate. I don't think I need that anymore, but it's okay. I can keep it there. All right, so we'll go to onlinegdb.com. And let me see if I have saved my project, because that would be kind of nice if I have saved the empty code already, then I can just kind of work on it. If that is correct. Okay, so we'll open the project. All right. All right. Okay, so this is the code. This is not the correct code. It is a piece of code, but it is not a piece of correct code. You know, if I'm not in a class, I would have a certain colorful description of what this is a piece of, but I cannot say that in class. So, so we'll start with, as long as the exponent of 10 is less than 0, we stay in the loop. And then, so one way you can basically start to understand how to write program is if the condition is something like this, that means something inside the loop body has to make changes to whatever is involved in the comparison. Okay. Now, if the comparison refers to 3 different variables, you may be making changes to 1, 2, or all 3. That's possible. But in this case, we only got one member of the structure that is referenced here because 0 is a constant. I cannot change 0. The only thing I can change in the condition on line 126 is the E10 member of the structure. So that means something in the loop must be making changes to that. All right, so we'll go like, okay, fine. I think we know what we are supposed to do here. This thing is supposed to increment, but the only way we can do this increment is because we do something to the coefficient. So now we have to say, we have to do something with the coefficient in order to allow us to increment the power of the exponent of 10 by 1 without changing the value the whole thing is representing, right? So the first thing is we can divide it by 10 because if one is division by 10, the other one is equivalent to multiplication by 10. We kind of cancel out and we are preserving the value. But we can't do this either because division by 10 without rounding means we have a bias that is only going in one direction, and that's one of the things that we don't want to happen. So we talked about the trick in the previous class that we can just do something like this. We use Pn points to coefficient. We add 1/2 of what we're dividing it from. We add 1/2 of the divisor before we actually do the division. So this performs the same thing as rounding, the division by 10 without using the float or double function. So we talked about this already. This is a technique that we talked about. This is all coming from just algebra. Okay, there's a lot of algebra involved in the writing of this code. So now the problem is, we can do this up to a certain point, but before we do the division by 10, we want the coefficient to be as large as possible. The coefficient itself as a member of the structure is a 64-bit unsigned integer. So that means we have to somehow say as long as the coefficient can be doubled, we want to stay in the loop here and keep doubling it. Okay, so we want to say, all right, let's go ahead and double the coefficient. And there are many ways to do this. This is the faster way to do it, or it is going to be efficient regardless of the architecture. Multiplication by 2 works too. So it's up to you to decide how you want to do this. And we have one more person joining us. There we go. All right. And because when we multiply the coefficient by 2, we want to preserve the value being represented, which means the exponent of 2 needs to decrement. Does that make sense? You multiply with the coefficient, you have to adjust the exponent, in this case up to 2, so that we are preserving the value that we are representing. So now we can say E2, you need to decrease by 1, decrement. So the question is, what do I need to put here? Okay, this is the tricky part, because what we really want to express, okay, taking into consideration the +5 and the division by 10. So what we really want to make sure is we want the coefficient times 2 plus 5 to be less than or equal to the maximum. And we know the name of the maximum already. I talked about that. I cannot even remember how many times. So this is the macro representing the largest value that you can represent using a 64-bit unsigned integer. So if you tell your math professor, this is what we're trying to do, we want to stay in the loop as long as it is less than, not less than, or equal to, because if it's equal to, then we are already maxed out. So it's less than, not less than, or equal to. So if you tell the math professor, this is what we need to do to make sure that we keep doubling the coefficient as long as there's room to do so. Your math professor will look at this and go like, yeah, that makes sense. But in computer science, I look at this and go like, no, that does not make sense. Because there's only one single value that is not less than the U in 64 underscore max. And can you guess which value it is? Same value. It is itself, right? U in 64 underscore max is the only value that is not less than itself. Otherwise, it would not have been called the maximum. Does that make sense? So, and then I think last time, did I mention your division by 2 on both sides in class? Or did I just say algebra? I think I just said algebra, yes. So I think most of you understand that, okay, we can divide it by 2 on both sides so that neither side can exceed the largest value that you can represent using 64 bits, right? So, and before we do that, we can do some, algebra too. So we can do a subtraction by 5 over here, get rid of the plus 5 on this side. Then we can finally, this is what we were really trying to get rid of, the multiplication of 2 to the coefficient. Because if the coefficient is already more than 1/2 of the largest or the maximum of a 64-bit unsigned integer, and you multiply by 2, it's going to exceed what we can actually represent using 64 bits. C and C++ does not give you an exception. It does not complain at all. It will just quietly give you the wrong number or the wrong answer, okay? So that means, now we need to get rid of this multiplication by 2 by dividing both sides by 2. So on the left-hand side, division by 2 simply means we get rid of the multiplication by 2, but on the other side, we actually have to add a division by 2. So this is the condition that is going to be true if we want to stay in the loop. So if I were to just do this, okay, I would get partial credit. I would not get full credit. Why? Well, let's check out what's going to happen here. Okay, so we'll put a breakpoint all the way down here, and then we debug the program. And I got some errors here because forgetting a close parenthesis would do that. All right, try again. And we have, oh, there we go. We'll try again. And then we are going to run the code. So r-n 1.23e -45, because this is what the log file is all about. The log file tells you how the coefficient E2 and E10 should change over time. Now, it doesn't tell you the structure of the code because guess what? That's your job to find out. But it does give you a sequence of how things should be updated so that you can use that to help debug your program. Okay, so we'll go ahead and say, okay, is that going to work? And at the breakpoint, we say print, asterisk, pn to find out what is in the structure. And you compare this answer here. Some of you may not be able to see it, but that's okay. I can describe it. It's not quite. It matches, I think, the 5th entry from the bottom of the list, but it's not quite all the way to the end. The reason is because this is not, if I double this number, it is not going to exceed the 2 to the power of 64 minus 1. Because I just divided that value by 10. I had a number where it is, if I double that, it would have exceeded 2 to the power of 64 minus 1. But because the last thing that we did was to divide that number by 10, essentially, the plus 5 really doesn't do a whole lot, okay? So once I divide it by 10, it's not going to meet that requirement anymore. So that means I need the code to keep doubling it again until I cannot double it anymore. So is that okay? So if this is the answer that I get, okay, I will give it a 3 out of 4. It is a B answer, which is equivalent to an Amazon review of 4 stars out of 5. It's pretty good, but not perfect. Okay. So to fix that problem, I just have to, yes.
Just to break off the discussion real quick, how do you skip past the breakpoint? If you have 2 breakpoints, how do you get to the second breakpoint?
Continue.
Just continue.
Yep, continue. So now I just need to replicate this code here. It is not exactly the replication because this time I don't really need to -5. I just have to say this has to be less than U and 64. Okay, I'll just copy this and then remove the -5 because I don't have a +5 anymore at this point. So that means the rest here is really just, okay, we'll go ahead and double the coefficient and then subtract 1 from the exponent of 2. And that's one of the solutions. That's one way to do it. Yes.
You still need to divide that by 2, right?
Hmm?
Because otherwise it's gonna multiply 1 past the max the last time.
No, this would be right. This would be correct. Because by the time I get out of this loop here, yeah, you're correct. The division by 2 apply to the maximum side. Yes.
And are you doing E10 plus?
Nope. No need to do any E10 because
No,
E10 is done.
Sorry, I'm like a syntax question. If you're doing E10 plus, would you also want to do E2 minus just for like consistency?
Well, you can do it any way you want to.
Okay.
Just for the sake of being rebellious, I'm going to do this. Or better yet, I will do something like this. How's that? Making the code looking so inconsistent. It's like, Dad, what are you thinking? But it is important to understand why. I mean, I understand it's good to have the code inconsistent, but at the same time, my job is to make sure that you guys understand, oh, you know what, this is the same as that is also the same as that over there, and so on. So this is really doing the same thing. It's just ugly. Yes.
There's a +5 on the second, I guess the third while loop.
Which line? That's the reason why there are line numbers here.
136.
136.
There's a +5 there. If you don't exclude it, how are you getting the 2 points?
You mean this one?
No. The
This one?
max, yeah, that one. If you don't include that on the third one.
If you don't do that, then you are basically running a piece of code that may get into trouble every once in a while. So the question is, do you want this kind of code running on your Tesla?
Yes.
No.
Very occasionally, when you hit the brakes, it just accelerates. So you tell me, right? For the most part, we'll give you 5 star out of 5. But the one time you get into the accident, you cannot downgrade it because you'll be dead. Yes.
Wait, can you explain why you use the +5? Why do you use the +5 though?
You mean here on line 134?
No, but
You mean here, -5?
yeah, what's the significance of having +5?
Because this makes sure that, even after doubling, I still have the room to add this 5 without this thing here being out of range. Because there's a very slight potential that it can potentially get out of range. So the question is, what is, yeah, go ahead.
For the inner loop for the condition, would it also work if the n arrow coefficient is less than 2 times pn arrow coefficient? Because it would mean that if it ever overflowed, the condition always fail.
Can you tell me where you put the code?
Line 128.
And how do you want to propose to change it?
If you put instead of which have there, just put pn arrow coef is less than 2 times pn arrow coef.
That will not work either because there are cases where this cannot detect the overflowing condition. So it would detect most of them, but not all of them. So the answer is no. This is not a proper answer either. So we are getting into the discussion, like the code that we are currently talking about on line 128, and also the question of whether the -5 is really essential or not. We are really talking about, is a piece of code that is mostly correct okay or not? That's basically what we are talking about. So if you're talking about an app, a mobile app, where, it's just an alarm clock or something like that, sure, maybe there are certain days, your alarm clock just simply does not work and you're late for school, okay? So it's not catastrophic, right? But on the other hand, if this code is running on something that is a lot more important, such as the program that is cranking out the social security checks, I think the cost of this kind of bug is pretty high, even though it doesn't happen very often. When it does happen, it is really bad. So I think as a software engineer, we really should try our best to make sure that we cover all the cases. Yes.
So grading wise, are we closer to the alarm clock or closer to like a machine that distributes morphine to hospital?
So if you miss the
Like the -5, if you didn't have the minus
five here, I would say,
is that a 3 or is that like a 3.7?
I'll give it a 3.5-ish kind of grade out of
So
4.
closer to the morphine.
Yes. So it's not quite, down to 1. I mean, if you think about it from the consumer perspective, right? If you buy something and it works most of the time, but the one time that it stops working is critical, okay? It causes, like people to die, okay? How would you grade the product, right? Yes.
I was thinking, when you put the -5 after it divides by 2, that's the last thing you would do.
Mm-hmm.
Because if you put it on the inside, doesn't that skew the +5 to like 2.5, which truncates to 2?
No, because I think you have to do that. It's like if we, so I actually thought about this. If you use the test case of like 100, right? Then 100 minus 5 is 95 divided by 2 gives you 47.5. And that'll work as long as anything that is less than 47.5 will work for the doubling. Because if you do divide by 2 and then -5, then you only get 45, but 47 works for the equation when you add the 5.
So I think the question is, it's a mathematical question. It's like, what was the original idea of that condition? The original idea of the condition is if I double the coefficient and add 5 to it, I should still be within range, right? So that means the +5 is after the doubling. It has to be that way. So when we apply the algebra to move things around a little bit, we do have to make sure the -5 is applied to the maximum first, because that's the outermost operation when we do the reverse operation. So when you have a compound function, then the inverse function is going to be in the reverse order. So that's why, we have to do it in this particular order. Yep.
So my while loop on line 128, I didn't do sorry, I can't tell. Is that a minus or +5? That's a -5, right?
This is the -5 here.
I did pointer to a coefficient is less than UNT max minus a pointer to a coefficient.
Minus what?
Minus the pointer.
Well, minus the pointer, or sorry.
Oh, minus the coefficient?
Yeah.
Yeah.
Okay,
And
so,
see, and then I
okay.
added 5 later, so I didn't have a -5, but I still got all the correct answers.
based on the test cases that we have. Okay, so now this is going to be a good exercise for all of you, okay, is to say, well, is this really going to matter? In other words, is it even possible for tech or anyone to come up with a test case whether the -5 is going to matter or not? So I think that's going to be a very interesting, question, because you have to work your way backwards, right? So you have to work your way backward and say, okay, whether there's a -5 or not here actually made a difference. Can we construct a test case like that? So if the answer is no, there's no way to construct a test case like that. That means, this -5 really does not matter. But then we are using mathematics to prove that it really does not matter. We're not saying, yeah, it's unlikely to happen. We don't know whether it's going to happen or not. We really need to use mathematics to prove that no, we know for sure it will not happen. So I think that's a good exercise, because that requires critical thinking, because you're not trying to construct a test case to see whether you can make a case where the -5 matters or not. Yes.
Okay, so when you exit this first loop that you had, then like you said, you're like 5 steps to go still, right? Because you have to redouble it so that you get the right format.
Yes.
So in your formatting loop, you don't have a -5. Right,
Because
because you're not doing it.
because there's nothing
Okay.
that adds 5 to it anymore.
So then,
yeah.
if you move to the -5 outside of the unit max here, that would just like err on the side of caution. So technically you could double the value, but you didn't. But it would still get you the same outcome because you're still doubling enough times at the end there. You would just like double one extra time at the end, right? So it goes through a different process, but you get the same outcome.
Did it one more time. Okay.
Okay, so because you eventually correct the doubling using the final loop, it shouldn't matter if you err on the side of caution in your first,
Oh, I see. So you're basically saying if we added the same thing over here, put a -5 in parentheses here, would it still be correct?
no, well, it wouldn't be correct. But what I'm saying is it doesn't matter if because someone asked if the -5 is on the inside of the parentheses or on, or past.
Oh, okay.
I'm saying it doesn't matter because you're correcting it later on because you're redoubling it all the way up to the max. Because inside, you're just doubling it enough and then you divide by 10. Oh, you know what? It does matter a little bit because
It
you don't
does.
get enough precision because you're off by a tiny amount of precision because you
Yep.
could have doubled it more, which means you could be a tiny bit more precise.
Yep.
Okay. There we go.
Yeah, sometimes I have to ask you guys to say that one more time because the auditory input, is really difficult for me. In other words, my buffer for auditory input is very small. So by the time you're moving on to the second sentence, I'm still parsing the first half of the first sentence. So, they would just totally overrun my buffer. So that's why, when you guys talk, you kind of talk a little slower. Yes.
So what is the purpose of that final while loop? You don't have any more division to do, so you don't have any more error that you're trying to minimize.
Yes,
It's
but
multiplying by 2.
but this goes all the way back to how the description of the homework was presented to you. So when we go all the way back to the homework assignment, and let me kind of zoom in a little bit here. All right, so it has to do with the first bullet point, the resulting coefficient C, which is the member's coef, should make the condition blah, blah, blah true. So because I want to make sure that we are using X number of bits, and it's just easier to say, okay, we're using all 64 bits. So this way, later on when I need to normalize and actually format, and figure out which part are the fractional part of the mantissa, I know exactly which portion of the 64-bit unsigned integer corresponds to the fractional part of the mantissa. Now I could shift it the other way too, but since we are already having a pretty large number to begin with, I might as well just kind of make it the largest possible number. So this way I can always scale back instead of I wouldn't be losing any precision this way. Is that okay? All right. Any other questions? Nope. Question?
No.
Okay. Yes.
Just out of curiosity, is there a solution to this problem that only requires the first 2 while loops rather than having a third loop that's outside?
Oh yeah, there are many ways to do it. I have seen very interesting solutions with one single loop and a few conditional statements inside the one single loop, and then the conditions would also break out of the loop. So there are weird ways to do this. Look, at least to me, they're weird. Having a conditional statement to break out of a loop, in my books, is a bad idea. Okay, I do not use break, I do not use continue, I do not use go to, because the condition of the loop by itself should really indicate what does it mean to stay in the loop and what does it mean to get out of the loop. But to answer your question directly, the answer is yes. There have been solutions with one single loop and some conditions inside the loop to get the same thing done. All right, so are we good so far? All right. So if this is okay, we're going to move on to the next homework assignment, which is due on Thursday. So I definitely recommend people to get started with this one as early as possible. On one hand, I'm giving you a lot less time, because there's no weekend between the 2 homework assignments. And on the other hand, I gave you the solution of the negative exponent already. So it really should help with this new one. Okay, so we'll take a quick look at this new one here at the description. So you can see that it's about the same thing. You can actually reuse your negative exponent program to do this code here. The two programs really should not interfere because one starts with a negative exponent of 10, the other one starts with a positive exponent of 10. There should be no interference whatsoever between these two programs. So you can see it's about the same thing. We have the struct float 10 to, which is 10 to 2, pointed by parameter pn, blah, 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 blah. So it's kind of the same thing. In this case, the conditions of the correct solution are also exactly the same. Okay, the coefficient has to be the largest value where if you try to double again, it will exceed the range of the 64-bit unsigned integer. E10 should become 0 from a positive integer, and then E10 can be any integer because we want to preserve the value being represented by those components up here. So that part of the question is almost exactly the same, except E10 starts with a positive value this time. So the question now is, so how do we do that? Okay. So I'm giving you a trace to but this time the trace is a little bit in terms of the format. And the mantissa is actually the coefficient. exp10 is actually E10, and then exp2 is E2. So because I'm just too lazy to change the description. Okay, there's no search and replace in Canvas to change the description. I don't understand why, but it's not there. Okay. So if this is the number 1.2345678 times 10 to the power of 30 is what we start with, I want to end up with this thing over here. This is barely fitting within an unsigned 64-bit integer. I will get to you in just a little bit. exp10 is a 0, and then exp2 is 36. Go ahead.
Is this the mantissa or is this just the coefficient?
This should be the coefficient.
Okay.
So read it as if it is the coefficient. But since this was written a little bit, like a few years ago, and it is really a lot of trouble to change all the mantissa to coefficient.
Because
so
mantissa would be normalized, right?
Yes.
Okay.
Exactly. So you read the mantissa as if it is the coefficient. It's just me being lazy and not having to manually change all the mantissa references to coefficient. The easiest way to do it would be to copy and paste this portion, put it into a text editor, do the search and replace, and put the result back into Canvas. But I'm a little too lazy to do that also. Okay, so when you look at this, it tells you how we can do this. Okay, because the first thing you should know is how we are changing exp10. So when we look at exp10, it is starting with 22 and not 30. The reason why it's not starting with 30 is because the so-called mantissa, which really is the coefficient, is 1, 2, 3, 4, 5, 6, 7, 8, 9 without the decimal point. So by shifting this decimal point all the way to over here, we also have to make adjustments to exp10 or E10 so that E10 have to decrease 8 by 8 in order for the coefficient to become 10 to the power of 8 of its former self. Is that okay so far? So this is all math. So now the next thing you need to know is, okay, so when do we do the first adjustment of exp10? So we can see that we made a, okay, so this is actually skipping a bunch of steps here. So we managed somehow to turn the coefficient to something like this. And we managed to turn the exp10 all the way down to 11. In other words, I shifted the decimal point to the right-hand side another 11 times. Because in order to decrement E10, I have to multiply the coefficient by 10. There was still room, okay? From here, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 123,456,789. Okay, that value is way below what the maximum of 64-bit unsigned integer. So that means, hey, I can just keep multiplying the coefficient by 10, and each time I multiply the coefficient by 10, I decrement E10 by 1. I still got room to do that for a while. Until I get to the line where the highlighted cursor is. So until we get to this line here, and if I say, let's go ahead and try to multiply this thing by 10 again, that would exceed the maximum of a 64-bit unsigned integer. That's when I go like, okay, so what do we do now? I mean, we have already maxed out the coefficient as a 64-bit unsigned integer. So we can no longer multiply the coefficient by 10 anymore. So what do? I go like, well, we can do certain things. Okay, so what we want to do is to compare this line versus the next line. So we're comparing this line versus this line over here. You can see the mantissa changed or the coefficient changed, but more importantly, you can also see E2 went from 0 to 3. So what is that telling you? Yes, go ahead.
That it was divided by 2 3 times.
Exactly. So I divided the coefficient by 2 3 times. So why do you think I stopped only after 3 times?
Multiplied by 10 again.
Exactly, because that gave me just enough room to multiply the coefficient by 10 again, which is reflected by the next line, right? So the next line is pretty obvious that we just multiplied the coefficient by 10 because everything is exactly the same, except we got one more zero on the right-hand side. And by doing that, we can also decrement the exponent of 10 by 1, right? But by doing that, we are also just maxing out the coefficient. I can no longer multiply this coefficient by 10 again. So what do? I keep dividing it by 2 until I have just enough room to multiply the coefficient by 10 again. So this time, how many times did I divide it by 2? I divided it by 2 4 times because 7 minus 3 is 4. So not 3 times, right? So you can see how the E2 is now 7 when it was 3 before. So I had to divide the coefficient by 2 4 times in order to have enough room for another multiplication by 10. So we start with this, we multiply by 10, and as a result, E10 can go from 10 down to 9. Is that okay so far? So yes, okay. So it's basically the same stuff as in the current program, the one that you turned in today, except when we used to divide by 2, when we used to divide by 10, now we divide by 2. When we used to multiply by 2, now we multiply by 10. But the rounding thing still has to be there. So remind me again, how did we do the rounding thing? Exactly, add 1/2 of the divisor before you do the division. Okay, very good. So in this case, our divisor is 2. So you have to add 1/2 of 2 before you divide it by 2. I'm not going to bother to tell you what is 2 divided by 2. Okay, very good. Nobody was following up and go like, but what is that? What is 2 divided by 2? Yes, go ahead. Oh, sorry.
No,
behind you
you're
first. Oh, okay, all right. So Chris, go first.
Sorry. So is it okay, say if we take our program that we wrote last week and just make an if statement, like if E10 is greater than? Or...
You don't even need an if statement, because if you structure your loop correctly, which is while blah 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 points to E10 is less than 0, this one starts with E10 being positive. So you should not even trigger that code to execute at all. Now, on the other hand, if you say, while E10, blah, 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 E10 does not equal to 0, then yes, you have to fix up at this. Okay. Yeah, go ahead.
So in this example, you're starting at 11, and then you take the exponent 2 to 3, and then you immediately go down to 10, just
Right.
Just because you have space to. But you have so many zeros, you're not losing any precision by multiplying by 10 immediately, are you? Like, couldn't you go all the way to, like, couldn't you just divide by 2 until you have an odd number and then multiply by 10 to build it back up again?
I suppose you could, yeah, but that makes the code more complicated. And it only gives you slightly more optimal solutions when this type of answer happens, right? So if you want to do the optimization, go ahead, but I don't think it is going to buy you a whole lot in real life.
Okay.
Yep. I understand what you're talking about because multiplication by 10 has an implicit multiplication by 2 because 10 is 2 times 5. So yes, I can understand what you're saying, but in terms of the simplicity of the code, doing it this way, it's still a linear time thing, so you're only changing the coefficient of the time complexity. You're not really changing the complexity itself. So yes, but very good point there. All right. So in other words, this is the clue, okay, and also the solution of the homework assignment due today, combined with the trace that I'm presenting you here, as well as the explanation. That is the clue of how you can work on the new homework assignment, that is due on Thursday, right before class. Yes.
Speaking of the solution, can you go back to the tab along the?
Yes, absolutely. So we'll go back to the tab of this one. I'm not sure whether I can zoom in with this one. I can, but I'm not sure, whether it does anything. Suppose it's okay. Yeah, I can give you guys this one. I can just send it to you all by announcement. All right. So are we still doing okay so far? All right. So remind me if I forget, remind me to send this code to the whole class through announcement. So this way, if you want to, you can use this as a starting point, but you still have to fully understand the actual code, why I wrote the code the way that I did. All right. I can try to help you answer the question. What is it?
Oh, I didn't have my, I was sorry, I had talked in the hand a little bit.
Oh, okay. No, but I was trying to find out what the question was, so I can address the question.
Oh, we were just talking about how to code the next assignment. How would we would go about the code the next assignment?
Oh, okay. Well, let's do that after class. Because we're going to go to the lab and do the program. But it would have something like this one, except the 2 and the 10 are sort of reversed. Okay, but the approach is, well, if there's room, keep multiplying by 10 until there's not room, there's no room anymore. And when there's no room and E10 is still positive, then you have to use division by 2 to make just enough room for another multiplication by 10. So how you express that condition is dependent on how good you're with math. But I think that is well within what I can assume in this class, okay? Because it's really just comparison and linear type of math. So you want to make sure that you keep dividing it by 2 as long as there's not enough room for another multiplication by 10. Okay, so you kind of want to work out the algebra first, and then make sure that in the comparison, both sides of the expressions cannot exceed 2 to the power of 64 minus 1. So you have to use algebra to kind of massage the expressions a little bit to make sure that both sides would not exceed the maximum value. We good so far? Okay. I believe my notes here, the actual written notes in section 3.2.2 also talks about this. So you might want to refer to the written material in section 5.2.2. Yep.
So how accurate is this method of like holding floating point numbers? Like what percentage of all 64-bit floating point numbers are going to like actually be misrepresented because when we're dividing by 10, we're losing like a tiny amount?
Well, you can actually do this experiment. Okay, so what I would suggest you to do, when you have time, right? Obviously, you have the homework assignment lined up already. But what you can do is to take this solution, and I can tell you this solution is actually have more precision than the built-in conversion subroutine in C++. I can tell you that because I actually tested. But what to answer your question is, you write this program, you get the solution, use the one that I have used already, okay? Because that's the one where you just kind of copy what is the last value of the coefficient, what is the last value of E2, right? So, and then you get rid of the -5 that is highlighted here, you run exactly the same code, and then that -5 is not going to matter too much. This +5 does. So this -5, it will not make a difference in most cases. So, remember earlier I said, it would be a good challenge to try to find a test case where that -5 makes a difference. So which one are we talking about? Are we talking about line 128?
Well, I was actually talking about with all impact, because theoretically, right, we are still losing a tiny amount of precision. when we
You
divide by
mean
10, right?
the -5 here or the +5 here?
No, I mean, like, we're keeping it all as is. When we divide by 10, we are losing the last digit of the 64.
Yes, we are.
Right, so how much does that account for? Like, in how many cases does that actually make a difference?
Even though, this is as precise as it can get.
How much more precise would like 128 bits?
The error in the very end here is going to be plus or minus 2 to the power of -51 as the mantissa.
Okay.
So we are basically maximizing the entire 53 bits for the mantissa already. And that error is that one is the least significant bit of the mantissa.
I see.
For the positive lab, exponent lab, are the last 3 entries for the coefficient, because they're all like the same. The coefficient doesn't change, the exponent of 10 doesn't change, and the exponent of 2 doesn't change.
You mean these 3?
Yeah,
Well, that's because, the code that I wrote, just kind of went through. Yeah, so it basically just ends with this line here. Yeah, remember, these lines are not representing, the structure of the code. It is merely representing when things got changed. And in this case, I did not change anything, but I wrote, the code so that the cout, just cranked out, 2 additional lines. Good question. Any other question about the homework assignment? No questions? Okay, all right. So we are going to go back to the NAND gate thing. Okay, so we'll go back to the NAND gate. And what I need to do is to start up LogicSim. And this time we want to analyze what is going on when we change the input pins of the NAND gate of the SR latch that we have talked about before. So let me go use a LogicSim first. So java-jar. All right. I'm going to put LogicSim into this window, so it's going to be recorded. And then we go back to the SR latch, which is supposed to be here somewhere. Not find it. Okay, let's check out here. Do I have the SR latch? No. All right, so I'm going to reconstruct the SR latch really fast. So we got 2 input pins, 2 NAND gates. So we have to go to gates this time, pick out 2 NAND gates. We only want to have 2 input pins for each one. Okay, so, and for tracking purposes, it is really helpful to name every single component, which I'll do next. So we have 2 output pins. And the context of doing this is the smallest and the simplest quote-unquote memory device that you can design using the logic gates that we have already been introduced. So And then this goes all the way here. And this kind of loops back. It's not exactly a loop per se, because it doesn't go back to the same logic gate. It goes to the other logic gate. But you can see how the two are kind of crisscrossed. Okay. So now I can go back and kind of name the components. This is known as S of the SR. This is the R of the SR latch. This is just a NAND gate here. We'll call this N1. And this is another NAND gate. We'll call this N2. This is one of the output pins. We'll call it Q. And this is the negation of that Q. In most cases, we'll call it NQ. There we go. Okay. So now we look at this, and the first thing I'm going to do is to turn off simulation. So I'm going to turn off simulation and reset simulation. So this way, we are not distracted by the result of the simulation, okay? Because I don't want us to be distracted by that. So I'm just using this as a way to kind of display the picture, as a diagram of the circuit. So what we want to do actually is to try to simulate what's going to happen to the circuit when we present, let's say, 0, 0, both as the input to the circuit. So that's the first thing we want to do. But we're going to do this in a very structured way, which means we are going to do this in a way where we try to use a very systematic way to figure out what is the next change, what is the next change, what is the next change, and so on. So I'm just trying to think of, how we can do this. What is the best way to proceed? I'm going to use a spreadsheet, okay? Anything that can do a table is going to be sufficient for this, but a spreadsheet can do exactly just that. So I'm going to use a spreadsheet. And here is my spreadsheet. I'll go ahead and resize the window a little bit just so that we can see the circuit. All right, so in the spreadsheet, what each row is representing is kind of like a moment in time. So each row is representing a moment in time. Each vertical column is representing the state of a port. Now, what do I mean by a port? Everything that you can connect a wire to is called a port. Okay. So we'll first name the components. Okay, so the first component is S, which is just a pin. So for a pin, for an input pin, we'll just say, whatever port it is connected to, is just a port. R is kind of the same deal. It only is an input pin, only has a port. Now, N1 is a little bit more complex because N1 has two inputs and one single output. So we have in bracket 0 as the first input, in bracket 1 for the second input. And it also has an output pin, but it only has a single output pin, so we don't need an array to designate to which output pin we are talking about. And we'll go ahead and make the columns as narrow as possible. And then we have N2. N2 is kind of the same deal. It has two input pins, in 0, in 1, and one single output pin. So all I'm doing right now is really just using a spreadsheet as a table so I can keep track of changes later on. And now we have two output pins. Q is an output pin. It also just have a port. And then NQ is also just an output pin, and it only has a port. So those two are fairly simple things to keep track of. All right. So this is kind of the layout of a table. The first thing we need to do is to say, okay, so what do we want to do with this circuit? So let's just say that we want to change both input pins, S and R, to zeros. Okay, so that would be the initial state. This is where all the changes start with. Okay, because the input pins are the only things that the external world can change within a circuit. So we can only start with the input pins. So we'll go ahead and start with the input pins. We say this is going to be a 0, this is going to be a 0. So now what do? Well, we do what we called a node propagation, or we want to use the node to find out what else is going to be changed because S and R as input pins were changed to zeros. So what we do at this point is we follow the nodes. A node is nothing more than a connection it can be a bunch of wires, it can be a single wire. But basically it connects the ports, it corresponds to copper on the circuit board connecting pins of the chips. Is that okay? Does everybody understand what a node is representing? So if you look into a circuit board, you see a lot of copper wires going everywhere. So if one particular copper thing connects multiple pins, then all of those pins, the copper is called a node connecting all those pins. So in this case, what we need to do, I usually call this one NC, which is node connectivity. Okay, so we're analyzing the node connectivity at this point. So we look at the S dot port and ask, who does it connect to? Who's going to get this 0 also? N1, the first input of N1 is going to get it. So we will say, you're going to get a 0 too. And then we look at R and we ask, okay, R, who are you connecting to using a copper wire? So that would be the second input pin of N2, like so. Are we doing okay so far with this part of the analysis? Everything else we can just say, don't know, don't know, don't know, do not know, and do not know. Is that okay? So remember, this is NC for node connectivity. Okay, we are basically just literally, visually looking at the circuit board and go like, if this thing changes, what else is going to change because of the copper wire connection? Is that okay? All right. So the next one, I'll call it a PD for propagational delay. In other words, this time we are asking if one of the inputs of the gates is changed after a certain delay, how is the output of that gate going to change as a result of at least one of the input pins changing? Yep.
Well, since you're putting zeros into NAND gates, it has to come out as true, right?
Exactly, because a NAND gate is a negated AND, and with a regular AND, if you have at least one input being a 0, the output is going to be a 0. But because this is a negated AND, so that means what a normal AND gate would give you as a 0, this one would give you as a 1. Okay, so you're absolutely right. So because input 0 of N1 is a 0, so I guarantee you that the output is going to be a 1. We don't even need to know what in1 is going to do. All right, and for the same reason, because in1, the second input of N2 is a 0, we already know the output is going to be a 1. Is that okay? So the PD row, or row 4 in this case, is really just trying to say, if we made a change to at least one input to one of the gates, is that going to change what the output of the same gate? And if so, how is it going to change the output of that gate? That is what the PD or propagational delay row is trying to represent. Is that okay? All right. So the next one is we're basically just alternating between NC and PD. So now we go back to NC. In other words, we are now looking at the changed output. Now, how do we know this one is changed? Because it went from unknown to a 1. That is a change. How do we know this is also a change? Same thing. It went from unknown to a 1. It is a change. So as long as it is changed, now I need to look at this pin or this port and ask, who is it connecting to? Now, this one connects to 2 additional things because the output of N1 connects to Q. It also connects to the first input of N2. So those 2 will be changed as a result of this. So now I can go to N2 in 0 and say, that's going to change to a 1 because this is a 1. And we can also go to Q and say this is going to be a 1. Are we doing okay so far with this? All right. So now we look at the other change, as a result of the propagational delay, and then we ask, how is the output of N2 connected to the other ports of other components? Well, the circuit is really symmetric, right? So by looking at the output of N2, in the diagram, we now say NQ is going to change. All right, so that's going to change to 1. What else is going to change? The input of N1 is going to change, or the first input or N0 is going to change to a 1 as well. So now we are completed with NC, or the node connectivity. So after a PD, we know how the output pin of some of the gates is going to change. But then we need an NC to figure out these output pins, where are they going? Who else is going to change as a result of these output pins getting changed? Is that okay so far? In terms of the concept? Okay. So now, yes, go ahead.
N1 get changed, if the N1 in 0 becomes a 1.
N1 in 0, it is changed by N1. Oh, you're correct. I put the 1 in the wrong column. You are correct. Good job. It should go there. It's the second input, not the first input. Very good. Okay. Very good. You were paying attention.
Yeah, I'm still confused, but.
You're still
I'm paying
confused.
attention.
Okay. All right. So now what do? We do another PD. Okay. Now, why do we need to do another PD? Because in1 of N1 got changed from a question mark to a 1. In other words, we have to ask the question, is that going to matter? This in1 here of N1 got changed from an unknown to a 1. That's a change. Same thing over here. The first input of N2 also went from unknown to a 1. So that means, I have to go for another PD to figure out whether the change of the input pins of these gates is going to change the output. And if so, how is it going to change the output? But in this case, the answer is relatively simple, because when we look at N1, at least one of the input pins is still a 0. So that means the output remains as a 0. So if the output is remaining as a 0, I don't even bother to put a 1 here so that I can remember it is not actually changed. Now we look at N2, and N2 still has the second input port being a 0. Even though the first one got changed from an unknown to a 1, we still have at least one being a 0, which means the output, it continues to be a 1. And that's it. Okay, we are done with the propagational delay with no actual updates this time. Even though the input pins of both of the NAND gates got changed, at least one input pin got changed, but that change did not affect the output. So the PD state is also done. So whenever the PD is reflecting, we don't have anything here, that means the circuit has reached a steady state. A steady state is a good thing. Okay, so we'll just go like this, OEM, and say this is a steady state. In other words, all the changes have fully propagated. Now it has reached a point where there are no further changes by itself. Do we have any questions? Are there any questions about what each row is trying to do? Or any, yes, go ahead.
So, you say NC stand
Node connectivity, or the analysis of node connectivity. So NC is basically saying, if I change this port here, based on the actual wiring on the circuit board, who else is going to be affected? That's what NC is trying to do. The analysis of PD, of propagational delay, is to ask, hey, I can see this gate has at least one of its input pins changed. How is the output going to be affected by the change of one of the input pins? So PD takes a little bit of time, usually measured in 5-10 nanoseconds. NC also takes a little of time, but it's a lot shorter because it really is just, you're just measuring when this end of the wire changes its voltage, how long does it take for the other end of the same wire changes its output? Even though it's not the light of speed, it is still really, really fast. So we are talking about way smaller than a nanosecond. So NC takes a very, very short amount of time. PD takes a little bit more time. All right. Any other questions? So I typically, talk about the nice states, after this. So this semester, I'm gonna mix things up a little bit and make a messy one out of this. Okay. So the next thing we are gonna do, okay, so knowing that we are currently in this state here, the next thing I want to do is to turn both S and R from zeros to ones. Okay, so I'm not saying, okay, you go to 1 first, and then you go to 1. I'm saying both would turn from 0 to 1 at exactly the same time. Okay, and we'll see, we'll try to find out why this is messy. Okay, so we'll say, okay, S port turn into 1, R port turn into 1 at the same time. Okay, and we always start with an NC here. Okay, so now we have to look at the the input pin R, input pin S, and we ask, okay, where are you connecting to by wire? So you guys can tell me who is going to be changed to a 1 because pin S changes to a 1. In 0 of N1. Yep, and then N2, oops. I just, my cursor is on the wrong window when I did this. Okay, so let me move the cursor back here. And then we have N2 in 1 also changed to a 1. Is that okay? Do you guys want me to color code the column so everything in the same node has the same color? Sometimes that helps. Yes.
Is it possible that you could zoom in a little bit at all?
Yes, I can.
You put it on the bottom.
Would that help?
That looks better.
And I can even make this a little narrower. That gives us a little bit more room to zoom. Is that okay?
That's perfect.
And I'm going to use color coding because I think color coding works for most people. So S connects to the first input pin of N1. The steady state is going to be a problem here. So I have to undo the merging. So we have to go to merged cell and unmerged. Okay, there we go. Okay. All right, so we'll go ahead and also get rid of the text because otherwise it will highlight this whole thing. So this is connecting, this is one node. Okay, we'll go ahead and color this. And we'll pick something like light yellow here. Okay. And then R connects to the second input pin of N2. So these two belong together and they would have the same color also. So we'll pick a contrasting color, which is light blue or teal. Blue, there we go, we'll choose blue. Then we have the output of N1 connecting to Q, which also connects to this first input pin of N2. So these three belong together. And we'll go to this tool here. We'll pick green. Okay, we'll take light green here. Nope, that's not light green. Light green, there we go. We like pastel colors. It's very pacifying. Easter. And I'm not even religious. So we have in1 going to the output of N2, going to NQ here. And we'll pick a different color. We'll pick something that's also contrasting. So maybe very light red. There we go. And it will also make sure that we have all the grid lines back. So we'll go to the grid tool. Where's my grid tool? Right there. There we go. Okay, that works. See, spreadsheets are very, very useful. Okay, sometimes we use it for calculation, sometimes we use it for illustration, and later on in the semester, it is also going to be our assembly. That is the fun part. That is the fun part. We'll be doing that in about 2 weeks, not counting spring break. All right. So this is our steady state here. Okay, this is our steady state. So now we are getting into a PD. So when you're in PD, you want to ask, is any one of the input pins changed? We don't care about the output pins. We don't care about the actual input pins. Okay, these input pins, we don't care because they're changed already. They're settled. We're asking about the input ports to the logic gates. So N1 has 2, N2 also has 2. Okay, so we are asking, is any one of those things changed? So we basically just have to go through each one and ask that question. So we go to column D and say, did it just change? Yep. Okay, if it's changed, we have to analyze N1. Okay, so that means we have to look into the output of N1 and ask, because the first input pin of N1 just changed from 0 to 1, is it going to change the output of N1? What do you think? Yes, it's going to change it because now at this point in time, both inputs of N1 are ones. So one N1 is a 1, but once you negate it, it becomes a 0. Okay, so we go like, yeah, we're going to have to change this one to a 0. And then we go to this one here. This one is not changed. Okay, so it's okay. But this one is changed because it went from 0 to a 1. So now we have to ask the corresponding component, which is N2, has an output pin. Is that output pin going to change? What do you think? It is going to change from a 1 to a 0 for the same reason. Okay, so that concludes our PD. And then we go back to NC again, because this time we look at the output of N1 and ask, because it got changed from a 1 to a 0, who else is going to be changed this time? This is where the color coding comes in here. Yes.
Okay, so why is the first set connected to the second set? Like why is SR being 0, 0 coming from 1?
Because I'm trying to figure out if I originally configured the input pins to 0, 0, and then I change the input pins to 1, 1, what's going to happen to the circuit? What's going to happen to the components of the circuit?
Okay.
So it's a continuation of the previous step. Because I just changed the input pin for the state of the input pins, F and R in this case, from 0, 0 to 1, 1.
So you weren't starting from 1, you're starting from 0, 0, then you change to 1.
Exactly. We are starting with 0, 0. Then we maintaining the state of the gates. We change only the input pins of S and R to 1, 1 in this case. That is correct. So thank you for that clarification. Okay. So now we're back to NC, but this time with color coding is a whole lot easier, right? This got changed, so all the green ones is going to change to zeros. So this is a green one, this is going to be green one. This one, wait. Okay, who else is changed to a 0? This one is changed to a 0. Okay, so all the red ones will also become zeros. So this is a red one. So is this one. So are we doing okay so far with what we are tracking and what each row is doing in the spreadsheet? We're doing okay? All right. So now the question is, did I just change something? Because if I did not change anything, then I'm done, right? Well, unfortunately, I did change something, right? Because look at this. Okay, I'm going to use the mouse pointer so that people online can also see it. Look at this one here. It used to be a 1. It got changed to a 0. Look at this one here. Nope, not this one. This one here. So this one also got changed to a 0, but it used to be a 1. So that means at least one input port of at least one gate got changed. So what do? We have to do another propagational delay analysis. Okay. So we do another PD here. So whenever you do a PD, you're looking for logic components or logic gates where at least one of the inputs has changed. We only got 2 logic gates, right? We only got 2 NAND gates. So we look at N1 and then we ask, the input 0 or the first input pin changed, over the last NC. No, that one, did not change. And then we ask, what about the second input pin? Yeah, we changed that. Okay, so that means, everything with the output of N1 needs to be updated potentially. Okay, so now we look at the output of N1, which is here, and then we ask, is it changing? And okay, this is not a very smart question. How are we going to change it?
Switches.
It switches back to a 1. Okay. Okay, but that's not the only one, because the last NC cycle also changed this one here. This is input, the first input of N2. It used to be a 1 until the last NC cycle, it changed to a 0. And it is one of the input ports of N2 as a NAND gate. So that means, okay, now we have to recompute the output of N2. So what do you think is going to be the current output? What do you think is the output of N2 right now?
1.
It's going to be a 1. Okay. Does that look familiar to you? We are now in the very same condition as in the row over here. This row over here is exactly the same as this row over here. But if people say, but I don't see a 1 here, that's because that 1 goes all the way back here. I did not report any non-changes. So if you see a blank cell, that means you have to go up until you see something that is not blank. Is that okay? So let's go through this one more time, okay? Because I know some of you are going to getting the idea already. But every time when PD ends up changing something, change from this 0 to a 1, change this 0 to a 1. So that means we have to go through another NC again, another node connectivity analysis, right? So what do? Well, node connectivity is an easy one. You don't have to understand what is a NAND gate. You don't have to understand what is exclusive OR and so on and so forth. You just have to understand, you just have to follow the colors. I was about to say follow the rainbow, but then it would be a Skittles commercial. I think the last time I watched anything that has a commercial in it was way pre-pandemic. And I can still remember the slogan. Follow the rainbow. Yes, we'll do that. All right. So everything that's green is going to update to a 1. All right. So this updates to 1. So is this one. But that's not the only thing, because the output of N2 also got changed from a 0 to a 1. So everything that's red also needs to change to a 1. So this changes to a 1. This one changes to a 1. Are we good so far? Yep.
Is this gonna keep flipping back and forth? Like,
Yes. It is impossible to get to a steady state because this one is called an oscillating circuit. So the circuit keeps oscillating between the two states.
Is that how it like maintains memory? Like this is the smallest form or something like that?
No, this is actually something that you don't want to end up with. But if you design the circuit like this, you will end up with that situation. And Logistic actually will tell you that oscillation is likely when you run the simulation like this. Yep.
Get the Christmas lights to put it.
Oh, this is going to be very fast. Okay, so if you just analyze the circuit here and focus on how the output ports are changed, you can see how it is in 1 all the way up to here. It maintained a 0 for only 1 NC and 1 PD cycle, and then the 1 is going to stay exactly only with 1 NC and 1 PD cycle. So that means you are looking at a blink rate where the period is measured in at the most tens of nanoseconds. Your eye can only detect changes in about 30 to 40 hertz. So this is way above what your eyes can register. Yep.
So would it just appear on and you wouldn't?
It would appear to be halfway on.
Oh.
Because you're looking at a 50% duty cycle. So it's on, off, but the amount of time that it's on is the same as the amount of time that it's off. So your eyes will do the average thing, and it will just register at 1/2 of the intensity. But your actual perception is logarithmic, so that means, things that are twice as bright it doesn't register as twice as bright, okay, because we naturally apply a log function to the actual physical image. We got 2 hands. Go first.
So what happens if we run that Watson right now? So,
What, in Logic?
yeah. Would it,
Okay, we can do that. I have to modify the circuit just a little bit to do that. Yes, go ahead.
Same question.
Oh, you guys just want to break it.
can you blame them?
Yeah, you have to link them because my hand cannot change both hands at the same time. So the only way to get this to work is to get one of them disconnected like first. And then we reconnect this one directly to the other pin, like so. So now, when I change this pin from a 0 to a 1, it would give us exactly the same effect as what we are seeing here. Okay, and I have to re-enable simulation. So enable simulation. This is good. Okay, remember, if both inputs are zeros, we don't have an oscillation problem. Both outputs would just become 1s. But when I changed the only input pin in this case, because remember, I changed the circuit itself a little bit. So if I change this from a 0 to a 1, then we have, okay, let me move this up a little bit. Oscillation apparent. So LogicSim internally is actually doing this kind of logic internally, and it detects that it is in a loop. Now, I don't know exactly how it gets it done, whether it is detecting I'm going back to the very same state, or whether it's just a timeout. Okay, which one it is, I don't know. Okay, but it has a mechanism of detecting that it is likely to be in an oscillation. Are we good so far? Okay, we're running out of time, but this is an interesting example of analyzing a circuit and understanding how to change this propagate, because this one does oscillate. Most of the time, we don't want oscillation. In this case, we ended up with an oscillation. Okay. So read the material, because if you read the material, it actually describes this process without using a table. It uses words to describe what happens when one of the input pins changes and whatnot. And we do not need an access code for the positive exponent assignment. So if you want to go home and start doing the homework assignment from home, you're fine doing that. But I'm going to go to the lab, okay? And if you have that obligation to be in the lab until 8:20 or so. So if you want to work on the program in the lab and get some help, I'll be there.
Negative exponent. So does it matter when it happens, or just at the final output for PN is matches the final output of the log?
Say that one more time.
Sorry. So the negative exponent one. So does it matter when E10 changes, or just that the final result is equal to the final one of the?
I only check the end result.
Oh,
Yeah.
because I just wasn't sure, because what I did was different. So before doing a loop, I didn't put the last loop, and what I did was at the beginning of this, the E10 to E2, I decremented E10 by 1 more, and then ran.
That's okay. I don't need to see it right now, because by the time I grade it, I would use test cases to grade it. And it kind of depends on, whether it works on the test cases or not.
And was there a role for today? Was there a role for today?
No, I did not take road today.
Okay, thank you. You have a nice night.